In order to start working with polyprotic acids, in other words, an acid that has more than one protic site, we're going to need a bit of notation that we can work with. So you can see here that just as an example, I'm going to use oxalic acid. This is going to be one of our common ligands that we'll see, and I'll bring that up in just a minute. Now, if we were to look up our Ka values, you'll notice that there's two different Ka values here, and that makes sense because we'll have one proton pop off. Now think through what that's going to do to our molecule. Now we have a negative charge. We're taking away a second proton. That plus charge has to get away from an existing -1 charge. That's not going to happen really easily. At least not so easily that it's going to happen automatically. In other words, we can have the first one be strong or not, and then the second dissociation will almost certainly not be a strong one. And in fact, when we go to our tables, we can see that in this case, Ka for oxalic acid is reasonably strong. The Ka for it's 5.6 times 10 to the minus 2, and that gives us a pKa value of 1.25. So, yeah, reasonably strong, but not completely strong. Second one, you see that that's going to be popping off somewhere around pH of 4.266. So, again, that's also going to be a pretty acidic proton. In fact, in deionized water, I'd expect both of these protons to pop off. But we'll get to that in just a second. Now, let's work through the notation here a little bit. You can see that pKa1, this is, unsurprisingly, the first one to dissociate. Now, obviously, it could have been either of those two protons. pKa2 would be when the second one dissociates. And if we were to try to position them along a number line, you can see that we're going to have one at 1.25 and one at 4.27. So if we were to position this, we'd want to have it at 1.25, right around there. Now for our other one, we're going to be putting that at 4.27. 1, 2, 3, 4.27, that's going to be right around here. Okay. Now, for our first proton, this is going to be pKa1. For the second one, this will be pKa2. When we're talking about the pKa scale, we start counting from the pH equals 0 side and work our way across. That's going to be the order that they dissociate as you get more and more basic in your solution. Now, we've also learned that we can be talking about pOH. And we know that pH plus pOH will equal up to 14. Now, that also tells us that if we're at pH of 1, pOH must be 13. In other words, it's going to just be a reverse of this process. So the order is just going to be reversed. Oops. Hard to talk and write at the same time. There we are. And just for completion, I'll go ahead and put in a couple of these just so you can see with your eye exactly what I'm talking about. Now, when we're counting across, we need to make sure that we have the right numbering for our pKb's. We always start from the direction that it's coming. So even though this is pKa1, and we're talking about the same proton over here, it will not be pKb1. We go to the basic end, we work from the basic end, and we say, this is the first one to grab a new proton. This will be the second basic site to grab another base. So this will be pKb2, and this one would be pKb1. Always make sure that you're counting them from whichever side that you're on. Now, that also means we need to be able to assign actual pKa values here, which we can do from right here on this table. And we need to be able to identify what our pKb's will be and correctly write them with the right number. Notice that we have pKa1 that's associated with this first proton. We know that its number will now be pKb2. So to calculate that, it would be 14 minus 1.252. So this will be right around a pKb of 12 point, and then the 7.5. Something right around that. And then for the other one, it would be 14 minus 4.2, I'm going to go ahead and round that to 7. So for this, I'd be at pKb equals, so 9.7. 7, 3. You see that these have to add up to be 14. These have to add up to be 14. Now, make sure that you're writing this correctly. This is a great way to keep track of things, to make sure that you're actually putting it with the appropriate proton. And I've gone ahead and rewritten it just so you can see that the B and the 1 should both be subscripts. You don't have to have B subscripted and then 1 be double subscripted. Don't worry about that. That's just kind of a silly way to do it. It's a great way to do it actually, but it's a terrible way when it comes to the easy typesetting. But I wanted you to see what we're trying to aim for when we write it. Now, I did mention that this makes a great ligand. Picture that structure for a moment with both protons dissociated. And notice that around pH 7, we will be at the point where both protons have dissociated. Notice that we have this tiny little pocket where we've got a double negative charge right there. You can kind of picture that it's going to be easy for something like a calcium ion to come in here and bind on very strongly. +2 to 2 individual -1 charges. That's going to bind on very tightly, especially with it wrapping around like this. And you can even picture that the electron density here, as this pi orbital gets delocalized, is going to make this very sticky for calcium. That's why calcium oxalate, I'll just go ahead and abbreviate that, equals something that's very painful. Kidney stones. Calcium ions binding with the oxalic acid will actually create a very insoluble product. I just wanted to point that out because that would be a case where if we have any calcium ion present, we would definitely need to use a systematic treatment of equilibrium because our chemistry turns very complex. Most of the time we're going to try to work in a regime where we don't have that complexity and we won't need a systematic treatment. Now, I also want to point out that when we're at very, very, very acidic conditions, way down in here, we're going to be in this area where there's so many protons around that any time that a proton pops off for the first time, this thing's going to bump right into another H+ sitting around in solution, and it's going to stick right back on. We know that's how equilibrium works. So when we're in the very, very acidic range, we're going to have H2OX. When we pass this pKb point, or pKa1, you'll notice that we're going to be at the point where the first proton's dissociated. Right here we had a 50-50 mix. Remember, that's pKa. After the pKa, we're going to have a tilted mix where we're starting to have more without a proton on it. So we're going to have HOX minus be the predominant form throughout this pH range. Now as we get closer and closer to the next pKa, or pKb, whichever way you want to think of it, we're going to be approaching the point where we get a 50-50 mix once again, but now it's going to be between HOX minus and OX2 minus. Once we pass that point, this will be my predominant species there. So we need to be able to identify the predominant species for each of our pH ranges. And we need to be able to identify it both in terms of the pH scale and the pOH scale. So make sure you can do your numbering in the correct directions. Make sure that you can identify your primary species. Make sure that you can convert between your Kas, your pKas, and also your pKbs and Kbs.